Okay, so how is everyone today? Good. Good? All right, so there's an exam in a week, right? Is that right? Yeah, 1 week on Friday. I guess there's really no good day to have an exam. So I guess Friday is as good as or as bad as any. But there's an exam on Friday. Good. So today's what, 26th? Okay, so we've been talking about sequences. We've been talking about sequences, and a sequence. What a sequence is it's a function from the naturals to the reals. So a sequence is a function. So, you know, if we name the sequence, usually when you make a sequence, it's like, well, let me say it like this. When you're writing functions down, that's a T. When you're writing functions down, a typical name for a function is f, probably because the word function starts with an f. But when you're writing sequences down, usually you write a or something. But I don't want you to get too emotionally attached to any of those names. So I'm going to say that the function the sequence's name is x. So it's x, and then the way that you write an argument for a sequence is instead of putting it in parentheses, like in the real-to-real case, you write it as a subscript. So usually that subscript is called n, but again, to keep you from getting too emotionally attached to n, I'm going to say a sequence is a function x subscript k from naturals to the reals. And so that's all that it is. It's just a thing. It's a function. It's a machine. You put a natural in, out comes a real. And some sequences, of course, are just are defined only on a subset of the naturals, like maybe just the positive naturals or something like that. So an example would be something like this. So ones that we want to know by name, anyhow, is it how about x sub k is 1 over k. So that's an example of one. Of course, that can't be defined for k as 0 because division by 0 is not defined. But again, this sequence, input goes to the output is the reciprocal of the input. That's so important that it has a name. What's the name of this one? Starts with H. Harmonic. So this is a harmonic sequence. We could have another sequence. How about P sub m is how about -1 to m. So its values are they alternate between -1 and +1, and as a result, what's the name of this thing? An alternator. But so this one is defined. You can define it at m is 0. What is -1 to exponent 0? 1. So what this is this is an alternator, and the first term is positive, and then the second one is negative. So this one is alternating between positive and negative, starting with positive. But here we've got a different one. How about r sub n is -1 to n plus 1? How about this? What is that one? That's also an alternator. But what's the distinction between P and R? Yeah, this one starts with -1 and then alternates, whereas that one starts with +1 and then alternates. Okay, and then if you say like H sub n, I guess, is equal to say -1 to n multiplied by 1 over n. You know. So what I want you to see from this is like a combination of two of the ones above, right? So that's an alternator, and that's the harmonic thingy. So what's the name of this one? Yeah, alternating harmonic sequence. All right. So there's lots of sequences. Now, we said the following. We said that we could say let AN be a sequence. Let AN be a sequence. And then we said that we say that AN converges to L and write that the limit as n goes to infinity of AN is L when for all epsilon greater than 0 there exists a big M greater than 0 such that little n more than big M implies absolute value of AN minus L less than epsilon. Okay. And then we made a joke. So look in your notes for the joke. It's from my point of view, it's like the highlight of the lecture. So understand what this definition means. Okay, a sequence when you plot it is infinitely many points. They're disconnected. So it's not like a real-to-real function like a parabola, say. It's not a continuous or differentiable graph. They're isolated points. So what this definition is saying, it's saying that well, suppose we have a sequence. Suppose we have some sequence. So this is the input axis, n. This is the output AN, right? And then we're saying that the sequence converges to some L. Now, the output axis is real, which means that I can select any of these are permissible, like even pi, something like that. So this is L. So that's an output value L. So that's a 0, 1, 2, 3, 4, 5, 6, right, etc. So those are the only inputs that are permitted. So like we can plug in 3 and we can plug in 4, but we can't plug in pi. So a sequence, if you plot it, is just some points there. The convergence definition is saying that all right, it's called an adversarial definition because you can imagine that there's two parties involved. It is like that I'm making the claim. I'm saying, hey, this sequence it converges to L, and then you challenge me and say, huh, well, if it converges to L, does it get within a meter of L? And then I can say, yeah. It will, but you have, this is how far out you have to go before you're always within a meter. And then you can say, well, is it within a centimeter? And then I say, yeah, but you got to go a little bit further. And then from then on, it'll always be within a centimeter. And no matter what measurement you ask, no matter how small but positive it is, I can always say, well, you got to go a mile to the right, and then you're good. So. If I'm the one making the claim, then you're the one that provides the epsilon. You say, well, is it this close? So what you're asking is that, is it always going to be less than L plus epsilon? and is it always going to be more than L minus epsilon? So what that does is it makes a in this plot here, it makes a strip. But what that is that's an interval of the outputs. So in the plot, it makes this strip here. So if I plot the sequence, remember it's just a bunch of disconnected points. So I'll plot and say maybe that's a point, and then that's a point, and here's one, and there's one, and here's one, and what have you. So notice that those ones that I've plotted there just arbitrarily, really. Some of them are in the strip, and some of them aren't. Okay. What the definition is saying, it's saying that you're the one that's in control of the strip. So you get to say how little it is. But then I have to be able to respond and say that yeah, I can make sure that all the points that we plot will be in the strip that you say. But we have to go out to this place over here. So once we get to here, so this is M. And what I tell you is that you make this small, and then I respond with that's how far you have to go. Okay, so then like this, and maybe even at the last second, that one's still no good, right? So it's like right there. But from now on, all the points are in the strip. So if, no matter how small you make that strip, I can always respond with the M, then you say that it converges. So just so that we have some terminology to be able to speak coherently about this. Notice that what M does, what it's saying, if you kind of consider a sequence to be like an infinite list of numbers, so like you can just list them all out, M cuts off finitely many of them in the beginning. So I might say, yeah, I can make it be within a centimeter, but we just have to discard the first million terms. But after that, it'll be within a centimeter from then on. Or we might only have to discard the first 1,000 terms, or even the first billion terms. We're just gonna cut this bit off, and then from then on it works. So, but beyond M, there's always infinitely many terms. Before M, there's always finitely many. There might be a lot, but there's only finitely many. As a result, this finite piece at the beginning, this is called a head. This finite bit of the sequence. And what do you suppose the beyond bit is called? Tail. So another way to say that a sequence converges to L is to say that for every epsilon, I can find a tail that exists entirely in that epsilon. Okay, so then we reminded ourselves about functions and limits and things like that, and then we said, hey, those real-to-real functions, if you know things about their limits, then you know things about sequence limits. Another thing that we need to see that we said was the squeeze theorem. We said the following. The squeeze theorem. We say let AN, BN, CN be sequences. So they're all sequences. If it is the case that 1, there exists a big M, which is positive, a big N, which is positive, such that AN is less or equal to BN is less or equal to CN, for all n more than m. Now, what we're saying is that we've got now 3 sequences. We've got 3 sequences. And what this first thing is saying that there's a tail. There's a tail of A, B, and C, of sequences A, B, and C, such that maybe we have to cut off the first billion terms. We just discard those. But after that, the terms in the sequences are always in that order. So they might be out of order at the beginning, for like maybe the first million years or whatever. But after that, they're in that order. So if they're eventually in that order, and the limit as n goes to infinity of a of n exists and is L, and the limit as n goes to infinity of C of n exists and is L. So if all of those things are true, so it's saying that if they're eventually in that order, and now because they're in an order to help us with the intuition, I'm going to say that that's the little one, that's the big one, and that's the middle one. So we're saying that if eventually they're in that order, and the little one converges to L, and the big one converges to L, then what about the middle one? It converges to L. So that's that's called the squeeze theorem. Conceptually, you can say that you can say it like because they're in the order little, big, little, medium, big, the little and the big one squeeze the middle one. Yeah.
Is it the same as the intermediate value theorem?
The intermediate value theorem is a separate matter because in that case you're talking about functions of a different signature. So this is about functions with signature naturals to reals, but the intermediate value theorem is functions with signature reals to reals, and moreover, they need to be continuous. And continuity is not a thing really for naturals. It doesn't make for not naturals, but rather sequences, because it doesn't make sense to ask, is a disconnected set of points continuous? So the answer is yes by any reasonable definition of continuous. But in some sense, the question is a little bit nonsense, because like these red points, those isolated red points, is that a continuous function? Now the mathematical answer is yes, but it's kind of not in agreement with your intuition. Like, can you draw that without picking up your pen? No, you can't. Okay, so then good. So here's an idea, is that we carefully we did the following example. We said let a of n be sine of n over n. And what we did is we set up, we observed that the minimum that sine of n can never be is -1, right? So the output of sine is always at least as big as -1. And what's the biggest that sine can ever be? 1. So then we said, oh yeah, that's actually, we can consider this to be the middle. We consider this to be between the negative harmonic sequence and the positive harmonic sequence, right? And the negative harmonic sequence, which is just to say negative 1 over n, the negative harmonic sequence converges to 0, the positive harmonic sequence converges to 0. The negative harmonic sequence is less or equal to that one. The positive harmonic sequence is greater or equal to that one, so this is the middle one. So where does this one go?
0.
To 0. Okay. So here's so I'm just reminding you that we did that. So here's something interesting. Suppose that we say let a n be a sequence. Let a n be a sequence. Let me think about this for a second. Let a n be a sequence such that the limit as n goes to infinity of the absolute value of an is 0. So instead of considering the sequence itself, what we're saying is that, well, compute each term, and then after that, compute absolute value. So like the absolute value of the alternating harmonic sequence would just be the harmonic sequence, right? Because the alternating harmonic sequence would have its sign alternating, but you're going to flip all of them to positive. Okay? So suppose that that's the case. Then the limit as n goes to infinity of just the regular sequence is what? Is what? No? It's going to be 0. Right? So the reason for this is sort of cute. It's a consequence, an immediate consequence of the what am I trying to say? Of the squeeze theorem. Is that isn't it the case? Isn't it the case that that an is less or equal to absolute value of an? Which is to say that suppose you have a number, then isn't that number less or equal to its absolute value? Yeah, right. Like is 3 less or equal to the absolute value of 3? Yeah. How about is negative 3 less or equal to the absolute value of 3? Negative 3. Yeah. So then that means that we can say that that one's bigger. Now, can you think of something that's smaller? So what I'm saying is we've got something on the big side. Can we think of something that's on the small side?
0.
Not 0, because this could be negative. That one. And you say, well, so this, what I've written right now, that's not true. That's not true because if an were negative, then that statement would be false, right? but if I just put that there, then now it's true, right? Now it's true. So we have that. That's sort of obviously true. And furthermore, since that is this thing is true by supposition, and because limit is homogeneous, which is to say that you can factor constants out, we can say that the limit of negative absolute value of an, we know what that must be. So since the limit of absolute value of an is 0, what's the limit of negative absolute value of an? Negative 0, right? Or 0, if you like. So here's the deal: is that this one, the one on the right's going to 0. The one on the left's going to 0. So what about the one in the middle? It's going to 0. Okay. So now, that thing we just said, we're going to use it in a moment, but I want you to understand that it's a little slippery. It's a little slippery because of the following. So notice that the following statement is false. So this one is true. This is true that the limit as n goes to infinity of absolute value of an equal to 0, that implies the limit as n goes to infinity of regular old an is 0. That's true. That is true. Okay. Now here's something that's not true. There's something that's false. The limit as n goes to infinity of absolute value of an, suppose that's equal to some other number, like 1, say. Suppose that's the case. Now, if I just sort of copied and pasted that line, just copy, paste, but then edited the 0 to be 1. So my question is this statement true? So this is a question now. Does that imply that the limit as n goes to infinity of just this is 1? That's right. In some sense, it would have to be positive 1 or negative 1, right? The reason why this works The reason why this works is that what's the negation of 0? 0. Okay, so then to see that to see the reason why this is false is consider I could say let a(n) be the alternator. Right? So a(n) is the alternator, which is to say that it alternates between positive and negative 1, and this particular one starts with 1. Then, if that's the case, then what is the absolute value of the alternator? One, right? Because the output of the alternator is either negative 1 or positive 1, but the absolute value of both of those is 1. So if that's the case, blah, blah, then I can say, well, the limit of n, the limit as n goes to infinity of the absolute value of the alternator is the limit as n goes to infinity of just 1. And what's the answer? 1. Right? This thing that we're looking at is a constant sequence. It's sort of as boring as it could possibly get. You know, this is 1. And every output is on that line. So I sort of like trivially, you can make the strip as narrow as you want. They all fall on that line. Whereas what about the limit as n goes to infinity of the alternator? What do we say there? What's the correct response to that prompt? It's not infinite. It doesn't go to 0. It diverges. It does not converge. Or you could say the limit doesn't exist. So this limit does not exist. So to make sure that you understand the meaning of that, remember the alternator is, you know, it alternates. This is more than just a clever name. So we've got, you know, here's 1 there, and here's negative 1. And the alternator does this. It's 1, and then negative 1, and then 1, and then negative 1, and then 1, and then negative 1, 1, right? So now, to show that it couldn't possibly converge, understand what it means to say that it does converge. You'd have to tell me. So now it's an adversarial definition, right? And if you want to tell me it converges, then you need to tell me what it converges to. So anyone say any number that I can plot there reasonably. What does it converge to? If you're going to make that claim. I mean, I just need just any old number. Yeah, so I just need some number that'll fit on there. 0? Okay, so you might say, let's say it converges to 0. Okay, for sake of argument, let's check. Could that possibly be the case? So that would mean that our claim is that it would converge there. So in fact, not our claim, but rather because it's an adversarial thing, it would be your claim, right? So I could say, well, can you get it within 10 miles of 0? And then, that would mean that, I've like lowballed one for you and said, I'll let you have the strip that's like enormous. So can you get all the points within this enormous strip? You can. But you have to be able to respond to any challenge that I throw down for you. So then, eventually it'll come to pass. I'll say that, well, can you get it like within the width of a hydrogen atom? Can you get it that close? Which means to say that I've given you a strip that is, this narrow. So I give you a little bitty narrow strip. And you have to respond, if possible. You have to say, yeah, if you go far enough to the right, then I can make sure all the red points fall in that strip. So can you go far enough to the right so that all the red points will fall in that strip? No. In fact, I've chosen a strip for this particular sequence, and for that particular strip, you can't get any of the red points to fall in that strip. And it doesn't matter where you put that point. You could put that point on 1, and then infinitely many of the points would fall in the strip, right? But infinitely many of them wouldn't. And you have to make it to where you cut it, and then for the tail, all of them fall in the strip. So this limit doesn't exist. All right, so it doesn't exist. Good. So for this idea, it's extremely important that the right-hand side is 0. That's extremely important. Okay. Finally, we have the following. We can say that let an be a sequence which converges to L. And let F be a function well, I have to say it like this: defined on an open set containing L and let F be continuous at L. So the further you get into math classes, the more like a legal statute these things start to sound, because mathematicians are kind of like the lawyers of the math science world. Okay, so supposing all of this, then we have the following: that the limit as n goes to infinity of f evaluated at an. So understand that there's two functions at play. There's two functions at play. The sequence is a function, okay, from naturals to reals. F is a function in the usual sense from reals to reals. And what we're saying is that we've made a composition. We've said, okay, we're going to pick naturals and we're going to give them to A, and A is going to do its thing and make an output. And then we're going to take the output of A and we're going to use it as the input to F. And we're just going to see what happens, right? Just as an experiment. Well, it's enough that if A is a sequence which converges to L, F is a continuous function at L, and the function is defined on an open set containing L, then what is this? So where is A of n going? A of n is going to L, right? An is going to L. So where's this going? To f of L. That's what it's saying. So what it's saying is that if the output of the sequence is going to L, then the output of f of that sequence is going to f of L. So I'll write it like this. You could say it like this: f of the limit as n goes to infinity of an, like that. So that's saying that, according to this, we'll evaluate f at every term of the sequence and then compute limit. So this is evaluate f first and then compute limit. Whereas this one is saying, just do the limit first. Go ahead and do the limit first. Don't even worry about f until the very end. You've calculated the limit, then do f. So this would be f of L. So it's saying that these two things commute. You can do f first and then limit, or you can do limit first and then f. So an example of this would be you know, something like this. I could say let h in be say, I don't know. Let me think. Yeah, so y'all aren't supposed to see this. This is my brain not working good enough to where I can do this in the morning. So I want this to be pi n plus 2 over 2n. You know, so just imagine that, you know, you can't see that. So let h of n be that sequence, and let f of x be say cosine of x. All right. Well, so the question then is, what about the limit? Calculate the limit as n goes to infinity of f of hn. Okay, so what I'm, you know, just as a sort of straightforward calculation, this would be, well, the limit as n goes to infinity of just plugging stuff in. Now this would be cosine of that thing there, pi n plus 2 over 2n there. And then, wow, I wonder if that expression inside of cosine simplifies it all.
Probably not.
Probably not. So then this would be limit as n goes to infinity of cosine, and then that simplifies. I can divide that into there, and then I get pi over 2. That's nice. And then 2 over 2n. That's 1 over n. Wow. And then concerning that sequence that's in there, so in the first place, is cosine a continuous function? Yeah, it's a continuous function. It's continuous everywhere. It's terrific. How about this sequence, pi over 2 plus 1 over n? Is that, so that sequence, is it a convergent sequence? Does it converge? It does. It does, because where does pi over 2 go? To pi over 2, right? What's the value of pi over 2 on Wednesdays? Pi over 2, right? So where does the pi over 2 term go? It goes to pi over 2. Where does 1 over n go? To 0. So this sequence is converging to 0. Is cosine continuous at 0?
Yes.
Yeah. So therefore, this is equal to in fact cosine of pi over 2 plus 0. And then what's the cosine of, you know, and pi over 2 plus 0 is pi over 2. And what's the cosine of pi over 2? 0. But, you know, if I had chosen sine instead of cosine, then the answer would be 1. You know? Any question about this? In the end, the whole purpose, the whole thing that I want you to see that's important about this thing here is that there's two ideas. Is that, you know, we've got sequences, which are these new kind of things, new kind of functions. And then you've got the old kind of functions, reals to reals. And you can compose them. Okay, and then compute limits of compositions and things like that. All right, making progress. So, in math, like in college algebra, there's something called the Fundamental Theorem of Algebra. So the Fundamental Theorem of Algebra is that every polynomial has at least one. It doesn't say at least one. It says every polynomial with complex coefficients has at least one complex 0. So it's what it's saying is every polynomial has to have some input that produces 0. And then an immediate consequence of that is that because you can also establish that zeros are equivalent to x-intercepts and equivalent to factors and things like that, it's saying that well, you find a 0. and then you perform a division, and now you have a polynomial of one less degree. So the fundamental theorem of calculus of algebra is saying that a polynomial of degree 7 has a 0. But then once you find that 0, then you can perform a division and get a polynomial of degree 6. And the fundamental theorem of algebra is saying that a polynomial of degree 6 has at least one 0. So you get that one, and then now you've reduced it to a polynomial of degree 5. Well, a polynomial of degree 5 has at least one 0. And you just continue, right? So then the fundamental theorem of algebra is more or less saying that a polynomial of degree n, where n is a positive natural, has n zeros. Okay, so that's interesting. And then, in calculus, we've got the fundamental theorem of calculus. The fundamental theorem of calculus says, more or less, it's saying that, instead of cutting up that shape, into rectangles and cutting it up into infinitely many infinitesimal pieces, and you've got to evaluate the function at all the points in the interval, like millions, billions, and even infinitely many evaluations. Instead of that, if the function is really nice, if it's nice enough to have an antiderivative, in fact, instead of evaluating the function infinitely many times to find the areas of all those rectangles, the fundamental theorem of calculus is saying how many times do you have to evaluate it? Twice. But you have to evaluate a different function. You evaluate the antiderivative once at the left endpoint and once at the right endpoint. So what's better, two evaluations or infinitely many? Two's better, right? But generally, the fundamental theorem of calculus is saying that you can exchange evaluation on the interior for evaluation on the boundary. So, if you were out in space, say, and there was some object that you didn't want to get close to, say like a black hole, because you'd be destroyed as a result, you can't safely approach a black hole, but nevertheless, black holes have an electrical charge, and you can actually determine the electrical charge of a black hole without actually having to fall in and measure stuff, because you'd die. The way that you do it is you just have to traverse any surface that surrounds the black hole. So instead of trying to measure the charge of the black hole by getting close to it, which is entirely not safe, you can just orbit around it a few times and just orbit a surface and measure the electrical potential all the way around, and you can determine the charge of the object. That's the fundamental theorem of calculus. It's saying that no, you don't need to go in there. Just go around it. That's enough. So here we have something. The reason why I'm saying this is that for every math field, there's something that's called the fundamental theorem of X. Okay, so then so here we are, and this thing we're about to say is called the fundamental theorem of analysis. Okay, the fundamental theorem of analysis. So apparently this one is important. Okay, so a couple of deals. So first, if I say that let set X be a subset of the reals. So we've got some subset. It might be an interval, but whatever you want to think. Then the minimum of set X is a little x in set X, such that X is less or equal to Y for all Y in X. Okay. So that again, sort of a definition that only a mathematician could love. So examples of this use, I could say, for example, what is the minimum of say the interval 14 to 24? It's 14. Sort of what, to view it as a picture, we're saying the following. Here's that interval. And we're asking, of all those points there, of all the shaded points, which one is least? 14. What about this one, the minimum of 14 to 24, but now it's open at 14? What about that? No. No. What's the correct way to respond to this? It's not 14. It's not 14 because the minimum of a set X is a number that's in that set. So can it be 14? So I'll address that in a minute. But can it be 14?
No.
It can't be 14. It can't be 14 because 14 is not in there. So the picture looks like this. So switching to color now, just as a visual aid. So this is 14 here, and this is 24. 24. And then now, what I'm asking is that concerning all of those red points, which red point is there a red point which is the smallest of all red points? And it can't be 14 because 14 is not red. So it can't be 14. So then you might say, 14.000, you might say that. So then you might say, well, I'm going to indicate some number that's like really super close to 14, like right there. You say, what about that one? And then I could say, well, I'm going to get out my calculus microscope, and I'm going to look at that, really look real close at what you're looking there, and I draw it at a really super inflated scale, so it's like really zoomed in. So at that level of zoom, here's 14, it's still there, and we can't even see 24, because it's like 5 miles over there to the right. It's like way far away. And however, wherever that is, at this scale, you're like pointing like right there, actually. So are there red points that are even smaller than the one you indicated? Yeah. So that one you indicated couldn't be the minimum. No, that because that's 14. That number you just said is 14. But that number that you're saying is 14.
Yeah.
So this, in fact, doesn't exist. There isn't a minimum. There isn't one. Nevertheless, if like, if you were on the street, and someone was like, like mugging you, and they showed you this set, and they said, I need you to tell me what the minimum is, and you said, well, it doesn't have one, but they're like, threatening violence. You might say, okay, you probably mean 14, and okay, and then they're satisfied. So we need a name for that idea. We need a name for the idea that yeah, this set doesn't have a minimum, but 14 is somehow important. Okay. So to that end, we need to be able to say, how do you say 14? How do you get to say the thing is 14? All right. So now we have something. Let X be in the reals, a set, be a subset of the reals. So a point A in the reals is called a lower bound. Of X when A is less or equal to X, little x, for all little x in big X. Now, as a picture, what that's saying is that, and I'll just use, I'll use that same set there. So now the distinction between the minimum definition and the lower bound definition is we're saying that the lower bound that we're talking about doesn't need to be a red point. It can be any old point. So how about like this point right here, which is maybe like a -4. Is -4 a lower bound of that set? It is. What about like -4 million? That one too, right? And then how about 10? Is 10 a lower bound? Yeah. What about like 17? Is 17 a lower bound? It's not, because even though it's less or equal to some of them, we need it to be less or equal to all of them. Now, how about 14? Is 14 a lower bound of that set? It is. It is, because we don't need to worry about it being red. So that's neat. So on this number line that's immediately below that one, I'd like for you to shade in the set of all lower bounds. So we've got like 30 seconds left. The set of all lower bounds is this. It's that. So now, finally, I can say we'll define L of X to be the set of all lower bounds. Of X. And so how about that set there? That set, does it have a maximum? What's the maximum of that set? 14. So the way that you say 14 is that you say, well, you must be actually asking about the maximum of the set of all lower bounds. And that idea is called infimum. So we define the infimum of set X is the maximum of the set of all lower bounds of X. And I want to impress upon you that what this is saying is that the set of all lower bounds is like the set of all little things. Set of all the little things. And then we're asking for max, which is the biggest thing. So infimum is the biggest little thing. And we can turn it around, and instead of saying the biggest little thing, we can say the littlest big thing. And that's called Supremum. Okay? Good. So have a nice weekend.